we have seen so far that how you can do the hypothesis testing when you do not have any idea about the population, right? You do not make any assumption about the population, and then still you can do the hypothesis testing using the Bootstrap method. And we saw how you can write the code for them in Python also. So now we will move on to the parametric case, where we consider that it might be possible that you do not know that it is coming from normal, rather it is coming from some other known distribution, right? Some other parametric distribution. It is not as if in the previous situation where you had no idea about the population. So here at least you have an idea about the population from which it is being taken. Now in such a case, if you are still interested in finding out the mean and you want to conduct a two-tailed test whether the population mean is not equal to this hypothesized value, then in that case also, first of all, you will be taking a random sample from this distribution. Suppose it is Poisson distribution, or it might be your exponential, any other distribution. So from these you take the random sample. Now based on this sample, you will find the sample mean and you will denote it by sample mean minus mu naught. So as we have done earlier only. Now what we do is that we estimate this theta which is present over here and we write it as theta hat. Now what you will do is, now you will be taking Bootstrap samples from this f theta hat. So if it is observed mean, so you will be taking from distribution with this new theta hat. It will not be from f theta. So you will now be resampling again and again with replacement from this f theta hat. So you will replace whatever the estimate you have obtained, you will replace the original theta by this estimate. And then you will find out your TIs. Again, you will have the same procedure. So xi bar, each of them will have the sample mean and then you will subtract the hypothesized value. Next, this step would be same. Again, you will compare the absolute value of this Bootstrap statistic with this absolute value of the observed statistic that you have obtained here. And then you will compute your p-value, which is basically the proportion of the observed or your Bootstrap test statistic are as extreme as or more extreme than what you have already observed, that is your t. And finally, you would reject the null hypothesis if p is less than equal to alpha. Otherwise, you conclude that you do not have enough evidence to reject the null hypothesis. So you can see that there is a minor difference from what you have done for the non-parametric case here, because you are not again sampling from here, right? This is the sample that you have obtained from some distribution, and this distribution has the parameter theta. So what you will do, you will estimate this parameter, and instead of now sampling from this or maybe sampling from this as we have done earlier, because in the non-parametric case you do not have any idea about the distribution, right? So you just keep on working with the sample itself. Now you have an idea about the population from which the sample is being taken. But now when you are taking the Bootstrap samples, you will not consider that it is coming from Poisson with parameter theta, but rather you will estimate, you will substitute it estimated value, and from there you will be generating the samples again and again. So that is the minor difference from the non-parametric to the parametric setup. Likewise, if I change from population mean to suppose variance, then also you can find out that, right? So test for single variance. This is sigma naught square. So what are we going to do? We are going to take a sample which is coming from some distribution, known distribution, other than your normal distribution. Now, what you will do next? It is about the variance. So you will be calculating the sample variance here, and your t will be basically that sample variance minus hypothesized value. Next, you are going to generate Bootstrap samples from f theta hat, right? So you will estimate this theta hat, and every time you will generate the Bootstrap samples from this one. Keep on doing that, and for each sample you will be finding out the sample variance. Okay, once you have obtained the sample variance, suppose for t1 to t100 you have found out the sample variances would be there, and then you will subtract from each of them, you will subtract the sigma naught square. Once you have subtracted and obtained it, You will take the absolute values of these TIs and you will compare it whether it is greater than the absolute this test statistic or the observed stat. So TIs are your bootstrap statistics and these are your observed ones. Finally, you will make the comparison. You will count the number of times the bootstrap test statistic is greater than, or extreme or more extreme than the observed test statistic, and you will find the p-value, which is basically the proportion, and you would reject the null hypothesis. So it is again very simple and straightforward. Likewise, if you have two means, what you will do? In this case, you are considering from two different populations, and the first one is coming, suppose, from theta 1, with parameter is theta 1 and here it is theta 2. For both of them, here you will find the sample mean, and here again you will find the sample mean, that is y bar. Suppose it is coming from Poisson with parameter, here it might be suppose lambda 1, or maybe you can say it is 4, and the other one is coming from Poisson, say 5. You will take the samples from them, you will calculate the sample means, and then you will take the difference of these two, because anyhow your D naught is 0. Again, you are going to estimate the parameters from your sample that you have, and you would replace those theta 1 and theta 2 by their estimates. So now you will no longer be sampling from here, but rather you will be every time sampling from theta 1 hat and f theta 2 hat. Okay, and once you do that, you will calculate sample means each time. You take the difference, you will get the bootstrap statistic, and then you can calculate your I value, that is the proportion, the p value, and you can finally make the decision depending upon whether your p value is less than equal to alpha or not. Next, likewise, you can do for the two population variances also. So same steps are there here again. Again, you are sampling from two different populations. First of all, you will calculate their corresponding sample variances. You will take the difference, right? This t will come. So as we have done earlier also for the non-parametric case, similar thing is happening here also. Then we are estimating it, and now the resampling is done from these new distributions, right? But distributions with your known or estimated theta 1 and theta 2. So here this one would be theta 1 hat and this one would be theta 2 hat. So I would be there. That is basically is the indicator function over here. So whenever it is 1, this is true basically. Whenever your ti, suppose t1 is greater than t, then it will give you 1. Again, suppose if t2 is not greater than equal to t, then it will be 0. Likewise, you can keep on comparing it, suppose till 100, and you will find out, suppose it is greater than equal to, so you will have 1. So you will count how many times these ones are coming, and that basically will be your I. And then you will take the proportion I by n, and finally you can make the decision whether to reject or not. So this is about variance and means that we have seen. You can do it for any other statistic in which you are interested, and you can consider any distribution and go ahead with it. And even if you do not have any idea about the distribution, still in the non-parametric setup also you can do the hypothesis testing. So this is how your Bootstrap works whenever you are learning for the hypothesis testing problems. So we will see now the codes for these parametric bootstrapping thing, and in the next week we will learn about confidence intervals. So let us now see how to do hypothesis testing in case you have a distribution other than your normal distribution. So we are considering basically parametric bootstrapping process. Earlier we considered the non-parametric situation. So when you consider the parametric bootstrap, so here let us suppose that we are considering Poisson distribution. So we are going to take the sample from the Poisson distribution. So let me write that. For the first of all, we are going to check for the mean. Okay, so test for mean in case of Poisson. So first of all, let us import numpy as np, and from scipy.stats import Poisson. okay, because we are going to work with the Poisson distribution. So now we are going to first generate a known Poisson distribution data set. So let the sample size, or you can first of all consider the true lambda be suppose 3.5. Next, the sample size, let that be 100, and data is going to store your Poisson random variables which are generated with this true lambda, and the size would be same as the sample size that we have, and we are specifying the random state to be 42. Okay, so basically we have obtained x1, x2, x100, so 100 data points from Poisson 3.5, right? So parameter over here lambda is 3.5. Now the first thing that we do in parametric Bootstrap is that once you have obtained the sample, we have to calculate the observed mean. So observed mean, that is x bar, would be np dot mean of this data, right? Then what will be the statistic we have? So for observed statistic we need the hypothesized mean. So let the hypothesized mean be, so let me just use a short form, hypo mean be 3. Okay, so this is the hypothesized mean, or I could just comment here that it is mu naught. And what do we have to find out? We have to find observed statistic, that is t. So that will be observed mean, that is x bar minus mu naught. So mu naught is basically hypo mean, or in this case it is lambda, so we are basically testing for lambda. So hypo mean would be, so let me just write this comment. So this is x bar minus mu naught. So we have obtained the first statistic. Now we have to write the code for the Bootstrap sample, how we will generate that, and we will calculate the Bootstrap statistic, that is TIs, for each of the Bootstrap sample that we have obtained. So for that, let us write the function to generate a Bootstrap sample. So definition, we are going to define Bootstrap sample. So data with the observed mean that we have taken, so observed mean. Here we are going to specify the sample. So sample will be generated from Poisson with this observed mean, and the size of the sample would be same as the length of the data set. Next, for each sample we need to calculate the mean. So again we are going to use numpy's mean function, and it is going to return the sample mean minus your hypothesized mean. Okay, because TIs are basically XI bars, so here these sample means are basically your XI bars, right? For each sample you will have the mean, and you have to look at the difference of that sample mean with the hypothesized mean. So that will give you TIs. Now you have to generate n Bootstrap statistics. So for that, let me write Bootstrap statistic will be. So we need to call this function here for I in range of your n. So n, let me define n also, so I can probably write here n suppose is 1000. Okay, so it's a large number of Bootstrap samples that we are extracting. So data, observe mean. So this is your TIs. Okay, let me just add a comment. So these are your TIs. So TIs is what? XI. So let me just write bar XI minus your mu naught. So these are your XIs. So once you have calculated the Bootstrap statistic, you are ready to find out the p-value. And what do we do in p-value? We look at the number of observations in which your bootstrap absolute value of bootstrap statistic is more than the absolute value of observed statistic. So ti mod of ti, is it greater than equal to mod of t? And then we will see for how many number of times it happens, and we will calculate the proportion for that out of total number of bootstrap samples that we have taken. So the p-value over here would be np.mean. So we have to find out the absolute value for the first one. So that is bootstrap st. Is it greater than equal to the absolute value of your observed statistic? Okay. Now you will set your alpha. Alpha is 0.05 suppose. So we are going to test if p-value is less than equal to alpha, then you will print reject h0, else it will print fail to reject. We can also see what are your values here. So let me just run this and show. Okay, so this is actually underscore. So we fail to reject the null hypothesis here. So we can also see what are the values. So let me just check what is the p-value here. Oh, sorry. So p-value is 0.537. So obviously it is going to reject because alpha is 0.05. And your observed statistic, we can also look at your observed statistic. That is 0.490. So this is how you can test for mean in case of Poisson distribution. So the idea is same in both the situations, with just the difference here that there you were given a sample. In non-parametric you have a data set and you do not specify the distribution and you just take the bootstrap samples from there itself. Now here, since we know we are drawing from Poisson say 3.5 and we are drawing a sample of size 100, so we specify that okay, from this distribution the sample is coming, and we specify that okay, how do you proceed in order to test whether the claim is correct or not. So in this case we fail to reject the null hypothesis, and we have obtained the bootstrap statistic by just following these steps, which we have done earlier also in the case of non-parametric. Okay, so in the non-parametric the difference was that we were not considering the distribution specifically. So likewise we can do for your variance also, or let us do for the difference of the two means. So we will import numpy as np, then from scipy.stats import Poisson. So because we are considering two Poisson populations, it means we need two lambdas, right? So true lambda 1 would be suppose 3.5 and true lambda 2 be 4. Okay, and the sample size, maybe I can just write small n, is 100. Now we have to draw samples from Poisson with 3.5 lambda 1, and from second one will be drawn from Poisson but with parameter 4. So Poisson, let me just write the command. So here random variables, here it will be true lambda 1 and size we have specified as n, random state would be again same thing we can do for the second group also. So group 2 here the difference will be in this case true lambda 2. So we have drawn two samples from these two populations. So here it means you have xi's and these are your yi's, y1, y2, yn, right? Now what will be the observed means in this case? Observed means, so observed mean for the first one would be np dot mean group 1 and observed mean 2 would be np dot mean for the second group. Sorry. So you have obtained x bar and y bar. Okay. Now you need to check the difference between these two because that will give you the statistic t. So for that, let me just write observed statistic as the difference between the two. Observed mean 1 minus observed mean 2. So we are finding out t equal to x bar minus y bar. Okay, so t we have obtained. Now let me also specify n, that is the number of bootstrap samples. Again we can check for this. We will define function to generate a bootstrap. So for that, bootstrap to sample, let me just write. So here data would come and the observed mean would come. So the sample will be drawn from this updated mean, because once you have estimated the parameter, then the bootstrap samples will be drawn from the population by substituting this estimated value. So here size would be n. So the sample mean here would be found out using np dot mean. Finally, it is going to return the sample mean. So this I have written for a single sample. So I will write this for two different bootstrap statistics that I have to calculate. So let me just mention that bootstrap st1. Okay, so this one would be basically utilizing the function that we have defined over here, and here observed mean 1 we will use, and for how many times? In this range. Okay, so this for loop will be initiated for 1000 times. So this is for the first sample, and here we will obtain likewise for the second one. Okay, so here we will write observed mean 2. Once we have obtained these are xi bars and yi bars, right? Because for when we call this function for the first mean, so here we will get the corresponding mean for the first one. So xi's, all the xi's will be there. So xi bars in fact, because this is a sample mean, and here we will get the yi bars. Now what we have to do, we have to take the difference. So ti is basically xi bar minus yi bar. So maybe I can write that again here. Bootstrap st would be the difference minus this st2. Now we can calculate your p-value. So p-value here would be calculated using this. We will consider the absolute value of this bootstrap statistic that we have, and we will compare this value with the absolute value of here it will be observed. So if alpha is again 0.05, we can check if it is going to reject the null hypothesis or not. So we can probably make use of this same command. Okay, so when you run, let us see what will you get. Sorry, so this is an array actually, so I should not do it in this way. So let me just comment it down here. So I did it in a hurry. So let me replace this. So one second. 1 minus, this is an array actually, so let me just mention here np.array for bootstraps st1 minus np.array bootstrap 2, sorry, st2. So first of all, these arrays, the differences, corresponding differences, and then the absolute value would be taken. So let me just, yeah, so you get failed to reject the null hypothesis, and the p-value is 0.52. So obviously it is obviously much more than. So you can see that what we have done primarily, and what is the difference from the previous one, that we were considering only a single sample, right? That is why here only itself we subtracted the hypothesized mean from the sample mean. But when we are considering two samples and the two populations, so here you don't have to subtract the hypothesized mean, because that would eventually get cancelled when you take the difference of these two. So we are just finding out xi bars and yi bars, and then we are taking their corresponding differences.